past, present, and what next. So today I'm going to talk about things that are being doing at the present time in the field of optical lattices. And so all the things I'm going to talk about are related to the fact of this achievement in the experimental side, which is atomic resolution in the measurements. So with the achievement of the quantum gas microscope for bosons and then for fermions, real space magnetic measurements are now available. And so there is a whole set of imaging and new physics coming out of it. And the study of not only spin correlations, but also charge correlations. And charge here is like an abuse of language because it's not actually charge, it's neutral atoms. Although the main interest is looking at antiferromagnetism as a first step towards superconductivity, studies start to drift away from half-filling and start to look at what happens when we have doping and filling. And then I'll discuss this Costelli-Towles transition because it's interesting when we have attractive interactions and both repulsive interactions. And so this is where I'll end today. So this is a sketch of the quantum gas microscope. So it's applicable when you have a 2D system. So many measurements of 2D materials are being made. And you have a layer, and then you have your optics on top of it, and the upper layer is measured. And I think I've shown this picture yesterday. So this is the 2009 article that have inaugurated the quantum gas microscope, showing in situ and atomic resolution measurements of the atoms. So here is like half the wavelength of the laser, and you can see here, whenever it's green is an atom and black is no atom. And so 2015, 6 years later, this was achieved for fermions. And as I mentioned, everybody, many groups at different places have been able to do this pretty much at the same time, 2015, all the papers here, and there is the potassium groups and the lithium groups, but it become, I wouldn't say widespread, because 6 groups in the world is not widespread, but different groups have managed to achieve this technology. And so everybody who could do this took a step back and started to looking back at the Mott insulator. Yesterday, I've shown in the first experiments, the Mott insulator was characterized by looking at average quantities, the double occupation, and here it's much more clear-cut. So you image, and then you digitalize, and you see things like that. So when you see something like that, you see one hole here and one hole here, but pretty much you see one atom in each side, and here the same thing. And this is the actual image, this is the digitalization, and you see the holes in here. And the holes in here don't mean at all that this is empty. It means it has a double occupation. So what happens here is that this is fluorescence imaging. So when you have 2 atoms in here, they form pairs, and they are ejected with collisions with the light that is doing the imaging. So what the first set of experiments that had achieved optical imaging, on-site imaging did, is look at singly occupied sites. So when we see an image like that, this is what we call, the theory people, a local moment. It can be either a spin pointing up or a spin pointing down, and this is what's being actually measured here. Or a singlon, a fermion that is alone in the sites. So atomic resolution for fermions was achieved. They saw the Mott insulator, so now is the time to look for real space antiferromagnetism. And not a coincidence, there is this number in Science, which was branded quantum simulation, and 3 papers in a row looking at antiferromagnetic or magnetic correlation. So I'll speak a little bit about each of them. The first one of them is from Marcus Greiner group, and what they did is here is an image of the trap in the optical lattice, and what they did is they removed either the up or the down fermions, and they had the image with the up, with the down, and without no removal. So they could, with this, comparing this image, know where ups and downs are, and with such, analyze the correlations between the spins. And this is a very nice plot. This is the whole density. And here is the nearest neighbor correlator. So this is very common to see in these experiments. They measure the correlation between one spin in a given site and its neighbor. If it is positive, they are both pointing in the same direction. If it is negative, they are pointing in different directions. And here we see that for most atoms here, it's negative and it's intense. So each atom has a near neighbor pointing in the different direction. And here we see that as at the edges of the cloud where the density is smaller, we start to have different things. And here is the diagonal next neighbor correlation. They don't have a plot here, but the lattice is like that, a square lattice. So we expect near neighbor to point in opposite directions, but when you look across a diagonal, you expect them to be positive aligned if you have an overall antiferromagnetic design. So this is what you see here. In the center, it's blue, it's positive, but it's less intense because correlations fall with distance, and we see here they fall pretty fast. This is much more intense because it's not too cold. As we get colder and colder, correlations start to fall slower with the distance. This is another of those papers. This is from Emmanuel Bloch's group, and he's doing this in chains. So it's a single strip, not a 2D lattice. And he developed something very, that became very important later on, which is using another mechanism. Instead of ejecting one type of atoms, either the ups or the down spins, he did a superlattice. And so in one of the, this superlattice potential, in one of the layers, he has all the ups and the other all the downs. And this allows for him to be able to see when you have a double occupation, which the others don't, because the others simply eject. Yes? Yeah, so as they have different they are different hyperfine states, you tune a magnetic field that aligns with only one of them. I don't know the details, but it's doable. And here you keep them both. And this is what he has seen. So he has been able to do longer distance, not only near neighbor and next near neighbor. They should oscillate between positive and negative. And here he has done this for 2 temperatures or 2 entropies. So when it's colder, it's more intense. The negative is more negative, and the positive is more positive. But you can see, once again, that it goes to 0 pretty fast. If you look at the 5th neighbor, it's already very close to 0. But you can see this up and down behavior. And he observes here with a -1 to the d to make them all positive, that they fall with the distance exponentially. And now I'll turn to the 3rd paper of that list, which is from Zwirline group. And what they have measured is both spin-spin correlations, so the spin in some site I and spin in some site J, and here usually first neighbor, and also the charge correlation. So what they have measured is the local moment correlator. And this is what we usually call charge, although it's not charge because it's an atom that's neutral. I'm just getting your attention for that, but it's it's a density. So this is the image of the cloud, and we can see here, you probably could see here, it's darker here, not in the center of the trap. So when you look at the local moment, that's measuring what you have here. You have a smaller local moment in the center, the maximum around this distance here, and then it falls down at the edge of the cloud. And this is just because here in the center you have a density which is larger than 1, and the atoms were ejected, so the local moment is smaller because it's symmetrical around half filling. When you have more atoms, it decreases, and it's maximum here when you have only 1 atom in each site, and then it decreases towards the edge of the cloud. And when you look at the local moment correlations here, you have regions where it is positive, regions where it is negative, and in the center it's positive. So it's kind of messy, and we'll try to understand that. And when you look at spin correlations, it's more easy to understand. They are always negative, meaning you have something like that. The near neighbors are pointing in different directions. So one thing that's very interesting about this experiment is you don't have to make any assumptions about the trap. I'm not sure you do remember yesterday I discussed Randy's Roulet experiment, where you have to know the density in each point of the trap to be able to calculate and measure the magnetic structure factor, because it's dependent on the density, and you have to know the shape of the trap. Here, you don't have to know the shape of the trap, because you can only measure the local moment in each point and plot everything as a function of this quantity here. So you don't have to really know how the trap changes. And this is one of these plots. This is what happens for spin-spin correlation. So we are looking at near neighbor. The blue points are the experimental data, and this green region here are quantum Monte Carlo calculations. And the idea of doing a region, the green area, is to pinpoint the temperature, right? Once again, the experiments, there is no way of knowing the temperature in a given experiment if there is no theory coupled to it. So this is a thermometer in this experiment. So we can see first that this is half filling, where the local moment is larger, and we see it becomes more and more negative as we go to half filling. It's 0 even when we have, and here is just with temperature. This is when correlations are off, so it's negative even when correlations are off due to Pauli blocking. But correlations certainly make the spin-spin correlations more negative. So they enhance this effect of having near neighbor pointing in different directions. And this is for the value of U over T that he used in his experiments. And so this is what I think is more interesting, is what happens with the charge. So this is the local moment. Yes? Sorry? So it's kind of a knob in your experiments, is by turning off the flashback resonance, so you turn off the correlations. But for me that do theory, it's very easy. You just turn U to 0 and you have the data. So the dashed line is like theory only. But it's just to have an idea, and this line here is also theory, but with U. It's just to show what should happen. They haven't done an experiment at U equals 0. So, but coming back here, this is the local moment correlation. And it's very interesting because it's non-monotonic. It has never been measured before, and actually it has never been calculated before in any system, because when we are doing theory, we kind of don't know where to look at. So when an experiment is done, it's kind of a challenge for a theory as well to go and get some new quantity. And this quantity is a particular challenge because it has many operators coupled to it, and then it's hard to calculate. But it doesn't matter, it's just you sit and you do the calculation. So what we see here is when you have small doping and small local moment, the local moments are negatively coupled. So what it means, if you have a local moment in one side and the density is very small, you don't want to have a local moment next to it. And so it's kind of, they repel each other, which is kind of unexpected to me. So the local moments are repulsive. They don't like to sit near each other. But on the other hand, when we are close to half filling in this region here, it's positive, and they like to be close to each other. So we have a bunching of local moments, and they become attractive. We try to look at it in more depth and see what's causing it. And here, at this time, Zwireline didn't have a way to see double occupation, separate double occupations from empty sites. And what happens here is that in between one local moment and the other local moment, we had empty sites. And this is why they kind of repel each other, because you wanted to have holes because the density was small. But this had not seen before. And so once again, the green area shows the temperature. This dotted line here shows U equals 0. And here is the minima position, and here the maxima position. So it's something that showed that, you know, local moments can either want to be close together if we are close to half filling, or be a part of each other if we are at low densities. And, but this is all only for near neighbors. So after a while, people start looking at longer range antiferromagnetic order, because if you have something like that, your near neighbor is pointing in the other direction. It doesn't mean that if you look at the whole lattice, this is going to keep having this organized behavior. So this is more recent work, 2017, and this is 80 by 80 sites. I'm putting the number here because somebody yesterday asked the size of the lattice, so 80 by 8 by 80, so it's a fairly large number. And what he has seen is that the correlations have reached the whole size of the lattice. So when you have something like that, what happens is, when you're at higher temperatures, you have your neighbors coupled antiferromagnetism. And as you decrease the temperature, you get the neighbor along the diagonal. And you decrease some more, and correlations reach further and further until you reach the whole size of the lattice. There is a very technical issue here, is whether you can call this long-range order or not. And the thing is, in two-dimensional systems, the true long-range order is only available at T equals 0. The Néel temperature, the ordering temperature, is 0 if you are in 2D. I'll discuss this a bit more. But the reason is the Mermin-Wagner theorem. It's very broadly based, and it says you cannot have order in 2D. And it has very wide implications. This, for instance, why a single layer of graphene ripples? It's not single layer, because it's not stable. It has to have ripples, because it would take a 2D system to be completely flat, to organize perfectly in 2D. So it has many implications, and this is not true long-range order. This is the size of his sample order, which is big enough. It's 80 sites. So, but anyway, just to make clear, you cannot have order through long-range order in 2D. So after that, experimentalists turned to look to incommensurate spin magnetism. So what happens if I, remove some of the atoms and leave some, empty sites here? So this perfect up-down order is obviously going to be distorted because you don't have atoms to have up and down in each one. And so you start to have a wavelength here that is repeated that can be, different than, not commensurate to your lattice. And this is a very beautiful experiment, once again from Emanuel Bloch's group, where he is, looking at the wave vector of this wave here that is trying to match the periodic organization of the spins in the lattice, and you see that you have some that don't quite match, the size of the lattice. So this is something that is very interesting, and people were trying to see, and this is the first time that it was seen. And as I am talking about, removing some atoms of the lattice, which is going beyond half filling, there are many experiments. I'm going to show only a few of them, but I selected two because I think they are really interesting. The first one of them shows string patterns, and this is very interesting because, at least to me, because this is not something we do in condensed matter theory, but as they can do this for and kind of photograph different ensembles, they have many images, and they can try to use some sort of advanced analysis pattern to see something we would not see in a real material. So they have taken pictures and removed it and seeing where the holes sit, and they found different patterns. And so sometimes they like to be close to each other, on the diagonal of each other. And if you analyze this more carefully, you see that you can have what they called sprinkled holes. I thought it was a cute name. Or some RVB-like states. So the RVB is like resonance valence bond. You have the ups and the downs linked close together and resonating, and the holes around it. And you have sometimes the holes surrounded by ups and downs. So another, possibility of imaging and analysis that is kind of very beyond what we can do in condensed matter systems. So I thought it was really interesting and worth showing you. And then the idea to study magnetic polarons. So for those who are not familiar, polarons is what happens when you have a charge carrier. And here, once again, charge is not actually charged, but it happens anyway. And it's dressed by the environment. So you have like a local polarization in the background because you put something in there. And the idea is to study that in the 2D Hubbard model. So you put a dopant, and you see how it bothers the antiferromagnetic regime that is there. And so here is this already pixelized image. It's mobile doublons. So these are like two doublons that are here, and they have this in a very tight space. I've underlined it here, 6 by 3 sites. So this is 3, this is 5, and how it affects what's around. And here is the image of the correlation. So the two doublons are here in the center, and this is affecting all the environment that's around it. And it's really interesting that you have the ability to pinpoint where they are and what they are doing with the correlations around it. So once again, this is something you cannot do on materials. And here is just another thing that they could do. They put a laser beam here and pinned this laser. And so this red is where the laser is focused. And then you create, kind of hold the doublons here, and you see the effects is similar here, but they are just more focused than they were before, where they appeared naturally. And so with this, people started to look, and so this is the same phase diagram I've shown yesterday for the cuprates. This is very interesting that this kind of phase diagram is in many of these experimental works in optical lattices. And so this is the temperature range where they are. So they are not here where superconductivity is. But they are probing what happens here. So here is the antiferromagnetic region. If you put just a few dopants, either you remove or you add, you had holons or doublons, you start to have this polaronic regime here, and then a crossover to some Fermi liquid, and this can all be probed within here. And they have been able to get this spin-spin correlation, hold spin. And so this is also a new development. Usually in condensate matter, we calculate two-point correlations. Spin-spin, charge-charge, spin and charge. But here, they are starting to measure whole spin-spin, whole spin-spin. So how these things couple beside pairs. So this is something that's also very new and only available in this kind of experiments, and leads to the possibility to probe matter in a way we were not able to do before. So I think it's quite interesting. And so a new development is doing the bilayer Fermi gas microscope. So I mentioned before when the first atomic gas microscope was done that we could not differentiate holons, double occupations, and double occupations. And in Emmanuel Bloch's group, where they did a single chain, they created a super layer, super lattice, where he could put one species in one layer and the other in the other layer. And in this, they would not eject the double occupations and were able to measure. And so here, this becomes available for 2D systems. So they have the bilayer, so they kind of split the layer in two and have only one kind in one and one kind in the other. And in this way, we have like here the brighter center that before was black, meaning it was either empty or doubly occupied, and now here it's brighter, it's not black anymore. So, and they can now differentiate double occupations from holons. And here is just theory, and these triangles here are experiments from Zwirline group. And so as this is now available, whole, local moment, whole doublon, density, all these correlations were not available before. And so we decided to probe them. This curiously came out just yesterday. It was printed. And so we can see we have the ability now to calculate and to measure all sorts of correlations, not only near neighbor as it's shown here, but beyond near neighbor. And this can be used to probe the state of the system at higher temperatures still. So here is what we expect in the Hubbard model, the temperature. This is U. So here we have this quasi-long range order that was probed in that Marcus Greiner experiment for large U and some temperature. But if we look up here, this is for T equals 0, we know what the system is in a MOT insulator with antiferromagnetic correlations, but as we increase temperature, we go from a paramagnetic metal to a paramagnetic insulator, and here we have this quasi-long range order. How do we probe from the correlations we can measure if we go from here to here? And this is an attempt of doing this. So this red curve here is given by the compressibility. So we calculate the compressibility and see when it goes to 0. So we call this metallic. And here is the density of states. They don't go to 0 at the same point. They only go to 0 together at t equals 0. But this is then the non-Fermi liquid regime. And here is the insulator when they are both 0. So this is a way of probing, you know, the crossover between this. This is not a real phase transitions. The phase transition is only at t equals 0. But as the experiments are done above t equals 0, we have to find a way within theory to explain the physics of non-zero changes across U and temperature. So another thing I think is very interesting is what happens when we have spin imbalance. So this is an experiment by Wasim Bakr, and what he did, he removed some of the ups or the downs, and then your system is polarized. And it's like, in theory, we have a Zeeman magnetic field that is going to favor spins in one direction over the other. When we have a theory or a material, when you put a Zeeman field, what you do, you turn your electron in the spin of your electron in the other direction, and you have more atoms in one direction, spins in one direction than the other. But here, you know, there is no field that is going to turn a hyperfine state into another. What happens is you remove and you add atoms in a different hyperfine state. And this here is probed with a wide range of polarizations. And doing that, what he measured is correlations along the z direction, which is perpendicular to the plane. This is a 2D arrangement of square lattice with lithium atoms, and both perpendicular to the plane. So, and they are different because of this non-existent Zeeman field, but because of the polarization. And so this is the results. Once again, the symbols here, the yellow and blue, are what's measured, and the dashed line and the dot points are theory. And so let me go step by step. The yellow are related to what happens along the z direction, perpendicular to the plane, and the blue to what happens in the plane. If you just look at these plots, you see when the polarization is 0, they are the same. The system is isotropic. But as we increase polarization, they are clearly different. The blue is more intense, either positively or negative, than the yellow. And the yellow here, you see it goes to 0 and it crosses 0 at some polarization. And we can calculate an anisotropy factor, which is just 1 minus the along the z direction divided by perpendicular to the z direction. And this is the near neighbor are here, is negative. And the next near neighbor is here, which is the very same thing here. So in the down part, the negative part, we have the next near neighbor, and in the upper part, which is positive, the next near neighbor along the diagonal. And here is the same. And the anisotropy we see is different if we look at the first neighbors or the second near neighbors. So what happens is, clearly, the magnetization is not isotropic. It's only isotropic here. And this is a cartoon of what is happening. So when we have no polarization, we have an isotropic system. But when we put this magnetic field, what we see is like the spins are canted. They prefer to lay on the plane than to be perpendicular to the plane. And this is an anisotropic system in 2D. And because of this anisotropy, we can have a non-zero critical temperature. And this is very interesting for experiments. I've mentioned before that when Marcus Greiner was looking into correlations, he said he had a long-range order, but he cannot have that because he is in this limit here, and the critical temperature here is 0. But as long as you break the degeneracy between out of the plane and in plane, then you can have this Kosterlitz-Tauss transition, and the critical temperature rises and decreases with magnetic field. And this gray line here is the temperature where the experiments are. So I'll talk a little bit about this. And this is very similar to what happens in attractive interactions. Let me just... So we have been discussing the repulsive Hubbard model, where we have a nu term that leads the system to localize and a T term that leads the system to have itineracy. And we have discussed a lot Mott transitions and magnetism. But what happens when we turn this U negative? So obviously, we're going to have pairs because the fermions are going to attract each other. And so we have pair coherence, superfluidity, and BCS and BEC, all this behavior that is happens. And so this is also something quite interesting. The attractive Hubbard model have been studied since the 80s. And in the beginning, what people did is, let's postulate this attractive interaction inside and just see what happens. And it's kind of phenomenological. In the repulsive Hubbard model, what happens is we have Coulomb interactions, and we disregard longer range interactions, and there is your repulsive on-site interaction. And here we had nothing to say, where this attractive interaction come from in the attractive Hubbard model, and the answer is, we don't know. And now we know it's from a Feshbach resonance that, the same way we have the repulsive, we can have it attractive, just tuning into a different magnetic field. So it's a realistic model within the framework of optical lattices. And so this is what happens if you have repulsive U. We have the antiferromagnetism and Mott insulating. And here, if you have the attractive U, you have the BCS, the BEC, if it's more attractive, superfluidity, preformed pairs. And so there's kind of a symmetry that I am going to explore more. And these two models, they are related. So if you take the operator that destroys an upspin with J site and do nothing with it, just keep it the way it is. But you take the downspin and you turn it into a the creator operator just like that. The -1 to the J, to CJ, and when you have this bar here on top is the changed operator. So I'm going to do nothing with the upspins, but with the downspin, I'll turn the destruction operator into a creator, and the other way around. And when I plug this into the Hamiltonian, this is what happens. So this is the original Hamiltonian in the presence of a magnetic field and chemical potential, and this is the attractive Hubbard model. So when I do this here, what happens is I turn plus U into minus U because of this sign here, and I turn the magnetic field into a chemical potential. And so if I have no magnetic field and no chemical potential, the two first lines turn into each other, and I have a half-filling SU2 model with mu equals 0 and H equals 0. But if I add either one or the other, mu equals 0 will lead to mu different than 0 will lead to a different density, so I go away from half filling, and a Zeeman field will lead me to spin polarization. So these two, oh, it came down, but this is here. So this change, this mapping of the attractive into the repulsive model has been probed in experiments. So this is a paper from 2020. And so this is the attractive part, and this is the repulsive part. And you can see they map pretty much on each other. And here, the balls, the circles are the singles, and the squares are the doubles. So we map the doubles in the attractive case to the singles in the repulsive case, and the other way round. So these things map onto each other. And coming back to the Mermin-Wagner theorem, this is a theorem that applies to 2D systems, and smaller or equal to 2. Here we are discussing this in 2D. And what it says is related to the number of components of the order parameter. So if you have the dimension larger than the number of components of the order parameter, then you can have TC different than 0. So this is what happens when we have like an Ising-like model, that spins can either point up or down. And then the number n of the components of the order parameter is 1, and then you can have TC different than 0 at 2D. If you have the number D, the dimension smaller than the number of order parameters, which is what happens when we are in an isotropic antiferromagnetism, that your spin can point in any direction, and you have X, Y, and Z components. So you have 3 components. It's larger than 2, the dimensionality. Then TC equals 0, which is what we see when we have isotropic antiferromagnetism or half filling in the attractive model. But in the case where we have the 2 of them being equal, so in 2D, 2 components, then you can have this phase transition in the universality class of the Kosterlitz, and it happens either when you have attractive U and away from half filling, or repulsive U away from isotropic case, when you have a polarization. So in these 2 cases, you have the same kind of phase transition, and it allows for temperatures, critical temperatures different than 0 in 2D. And if you go on and follow this, once again, these calculations, and see what happens in the spin-spin correlation functions, we see we map the Z component of the spin into the charge correlation functions, and the up and down spin correlations into the superconductivity or the parameter. So the charge and spin degrees of freedom are exchanged in these cases. So this is why this has been known for a while. This is a phase diagram obtained in the 90s for the attractive Hubbard model. And it was, if today you try, to publish a phase diagram with 2 points, I don't think you're going to get through it, but in the 90s you could. So, and it was very, very clever because, Adriana and Doug knew that the empty system, TC has to be 0, you have no particles. And they know, because of the Mermin-Wagner theorem, at half filling, it has to be 0 because of symmetry. So they have this, 2 points, and they draw the line. And I think it's, so clever. And here, what happens is the charge density wave and the superconductivity are degenerate. And so they added together, they have 3 components, and this drives the critical temperature to 0. But as soon as you dope it a little bit, they they have different energies, and the charge density wave has smaller, has higher energy, and you have superconductivity, superfluidity. So it's super fun. I've done this later and added more points, but you know, the points here and here are really pinned. But it's important to have, you know, a good estimate of these temperatures. And you can see here it's around 0.15. This is in hopping units, because people are going to do experiments and they want to know how cold they have to go to reach this place. So if we look at these two experiments, they, although it's kind of very different, attractive interactions, repulsive interactions, and you have canted antiferromagnetism and superfluidity, it's exactly the same physics they are showing here. So this shaded gray area here marks where the experimental temperature is in these experiments. Here we have the TC going to 0 at half filling in both cases. But I think the bottleneck is the important thing is it's the same physics. And so I am jumping to talk a little bit more about what happens when we have attractive interaction in fermionic systems. So this is a sketch of what happens when you are in the continuum, not in an optical lattice. And this is what happens when you have a lattice. And they are somewhat similar. So at lower temperatures, you have a superfluid. And also here, at lower temperatures, you have a superfluid. Here, if you are in the BCS regime, you have a normal Fermi liquid. Here is this T star temperature. That's a very important temperature when you have unpaired fermions. And when you decrease and cross this temperature, you start to have preformed pairs. And here you have your normal Bose liquid, because the pairs are already formed. So you have like a boson that's composed of two of these fermions, and they reach a certain temperature at which they condense. So this is like two different ways of achieving the superfluid. Here you have preformed pairs that condense, and here kind of it happens all at the same times. You have the fermions, and then they pair and condense all together. And this is what happens in the continuum. If you're curious, Mohit Handaria has done a lot of work in this system, so just look up for him. And this is a sketch from the 90s for the attractive Hubbard model. So this pretty much here, you also have a normal metal from which, when you decrease the system, you enter the superfluid phase. So you have both things happening at the same time. The pairs form and condense all together, and this is, once again, what we call the BCS regime. And here you have a phase where this TP is the pairing temperature, where we have pairs forming. And then you, in this region, you have this phase of uncorrelated pairs, and you decrease the temperature. It falls with T square over U, and you enter the superfluid region with preformed pairs. And this is what we call the BEC region. So regulating the intensity of the interaction, you can go from one region to the other. And this is something interesting. And so here is the same plot as before, but with numbers. It's not a sketch anymore. So this is the superfluid region is very tiny down here. And this is this line here, T, is the pairing formation. This dotted orange region here is where we have the degenerate Fermi gas. Here we have the Fermi liquid with unpaired fermions, and here we have preformed pairs that, when reaching down here, condensate. And this is a blow up of this region here that, you know, obtaining the critical temperature for a given density as a function of U over T. So I'm going to show you some result. Rodrigo Fontinelli was a student. He finished his PhD not too long ago at the UFRJ. He was not my student. He was Raimundo's student. But we've done some work together in the attractive Hubbard model. And I really like his work. And I see it's cited by, Zwirline, and it's kind of a validation of work well done. The experimentalists are looking at our data and doing something to it. And so what we wanted to do is use quantum Monte Carlo to find the critical temperature. Once again, we want to guide the experiments. If you don't know how cold you have to get to see these phases, so how are you going to, plan your experiments? And so we do this by calculating pairing correlations. So the pairing correlation is something like that. You destroy a pair in a site I, and you create a pair in a site J, and you see, how this falls with the distance. And here, beta is the inverse temperature. If you're very hot, let's say it falls very quickly. If you're not very cold, but cold enough, it stabilizes, and it means you're forming pairs, and your pairs are correlated along your lattice. And we use this to probe the critical temperature. So the fact that we are in a Kosterlitz phase transition, it has its peculiarity. So we know the finite size scaling when we are in this type of transition. The pairing is supposed to go with the L, which is the size of the lattice. 2 minus eta. Eta is an exponent that is known to be 7/4 for this kind of correlation, and here a function. And so we try to adjust the TC and here to have them all collapsed, and with that we extract the critical temperature. So it's a work sum, computational to extract a number which is the critical temperatures. And then this was done for value of U, a value of density, and we have to do this for different system size to obtain a collapse like that. And then we probe different values and see which one best adjusts to extract the critical temperature. And so he's done this for different values of U, different values of temperature, and came up with this nice phase diagram. Oops, let me come back. And so so this is the 3D phase diagram. This is temperature as a function of U for different densities. This is temperature as a function of density for different U's. And they tell the same thing, but it's nicer to look this thing here. Once again, we have to have TC going to 0 at half filling because of the Mermin-Wagner theorem. But he found this, which I find is very useful for experiments, is this sweet spot for experiments, the region where the Kosterlitz transition is, the temperature is higher. So around 5.4 U, and the density around, here, 0.8, 0.7. So you know where to look when you want to find a higher temperature. But there are other temperatures that are interesting. The first one we looked into is the pairing temperatures. We know that in the BCS phase, in the BC phase, we see the pairing forms, and then they cohere. And so finding the temperature at which we have pair formation was also interesting. So in experiments, what they do is look for the susceptibility, where it starts to go down, pair starts to form. So this is what we do here. We calculate the susceptibility, and the stars are at the maxima. And we also wanted to look at the degeneracy temperature. So we just looked at it here once again to obtain a more detailed phase diagram. So for each density, it looks a little different. We see that this is the pairing temperature in blue. The red dot is 4 times the superfluid temperature, because it's very small, so if we don't multiply, you can hardly see. And in here in green is the degeneracy temperature, which goes up and down a lot with density. So one thing we also thought, as the experiments now can be done in layers, if we add 2 layers, is it going to help increase the critical temperature or not? And so Rodrigo also looked at that. So this is what happens when you have a bilayer in red and when you have a cubic lattice in blue. And this is the hopping along the perpendicular direction. So you have 2 layers and you have a hopping T within the layer, but the hopping along between different layers can be tuned to different values. And we see that if we do this, there is an increase in the critical temperature, and it's kind of above 0.2, so maybe it's useful for experiments. So if we look at the temperature scales between theory and experiments, we see here, you know, what we found is the higher Kosterlitz temperature is around 0.15 in what we call the sweet spot. But in experiments that I've shown in 2017, 2018, it's here, 0.45, 0.40, so kind of 3 times above the critical temperature. So hard to, you know, these experiments are not going to see what's going on. But in this experiment that I've shown, you know, in the very first, when I very first started to talk, this 2025, like June experiment in Marcus Greiner group, he has reached this, what he called cryogenic limit. So this temperature is below this. He did not look at attractive interaction. This is not what he was looking for. And I don't know if he can change repulsive interactions into attractive interactions and keep the temperature that low. But if he does, he will see, you know, the superfluid phase. And so this is a major advancement. So I'm going to talk a little bit about the BCS-BEC crossover. So to characterize that, we are going to see, look at the double occupancy. So what happens is we saw in one case, we have no pairs formed, decrease the temperature, and the pairs form and get into the superfluid state at the same time. And in the other case, we had preformed pairs. So just analyzing the formation of pairs, we can see whether something is going on. And so here is what happens at a quarter filling density. And here is we are increasing U, and we are looking at the statistics of the formation of pairs. And here at 0.875, and we are also doing the same. And we see here that as we increase U, we start to have pair formation at some given value of U, here around 4.5, and here around 3.5, we start to have a lot of pairs forming at higher temperatures. And to characterize this BCS to BEC crossover, we investigated the Fermi liquid behavior. I really like this cartoon. The idea is you have a real particle and you have the dressed particle. So you have to figure out whether you have dressed particles or not. One way of doing that is when you have a Fermi gas, this is what happens. When you have some temperature, you move some particles that are here to the side. But when you are in a Fermi liquid, you have all the scales of interactions playing a role in here. And usually what is done is looking at the quasi-particle weight, which is the amount of which is constant here. And this is something we can calculate within Quantum Monte Carlo. It's not straightforward, but it can be done. And this is what we actually did. And so this is the quasi-particle weight, and we are marking its value here along the critical temperature. And we see that the Fermi liquid seemed to be lost along this crossover when the pairing temperature scale is crossed. One way of seeing that is in a Fermi liquid, the Fermi sphere is easy to see. We have a clear boundary of what is occupied and what is empty. So here, this is occupied and this is empty. But as we reach this high interaction, it's kind of blurred out. And so we are losing this Fermi liquid behavior as correlations are increasing, and we are crossing over from one regime to the other. So I want to talk a little bit about cloud density, because this is kind of the final bottleneck. Yesterday, I have discussed the harmonic trap confinement, which is just parabolic. I've told you a little bit how the trap in Hewlett's group is complicated because it has a Gaussian and then an inverted Gaussian. And we look at the profile, it's kind of a nightmare to the theory people, although it reached lower temperatures. But a major advancement, at least for me who is doing theory, is to have, you know, a flat, the possibility of not having a parabolic or a Gaussian or whatever, to have a flat trap. And this is obtainable through DMD. So this is a setup I have no idea how to explain. I just wanted to let you know that this is done with micromirrors. And I know Patricia has some of images like that. I think it's super cute. You have the faces, so you can design whatever shape you want. And this is a major also advancement. And this 2017 paper where Marcus Greiner said he had antiferromagnetic long-range order, what he had is a flat center here and here. So actually a fairly large region, 80 sites in his case, where you don't have variations in density. And this is why he was able to say, you know, I have an arrangement just like that over 80 sites. And so this makes a lot of difference. Then when you have, you know, the center of your trap filled with 2 sides, 1.9, 1.8, and you have a density that varies along the trap. So this is a major improvement and can lead to easiness to understanding what the physics is, because you can also, it's not that going away from half-filling is not interesting, it is, and we want to see, you know, superconductivity doesn't happen at half-filling, it happens away from half-filling, but we want to have a steady density. We want it to be the same over a wide region, so we can understand. It doesn't have to be half-filling as in his experiment, but it has to be constant over a region of the space. So the bottlenecks that were that I mentioned in the beginning were temperature, and now this temperature has been achieved this year. It's not clear to me if it's reproducible, you know, with attractive interactions, with spin imbalance, with other geometries, and what are the needs to reach this temperature. But this is clearly a very important achievement in the field, and it's going to open up, you know, lots of possibilities to investigate ordered states. Another thing is that local moments, doublons and holons, are not differentiatable. In the beginning, we only were able to see local moment in the Fermi gas microscope, and doublons and holons were mixed up and ejected. and now we know what is what, and this also make a lot of difference. We are able now to measure. We is very cute. I don't do the measurements, I do the calculations. But, you know, in the field, people do longer range correlations calculations and 3 points and 4 points. So there is a huge advancement. And the DND has allowed for constant density. So with this, cooling is solved, thermometry is solved still with the aid of theory, imaging solved, and cloud density solved. So we have all the tools now, and this is very recent because this cooling was, you know, June, and we are in November, October still, not November. So the future is now. I think it's a very exciting moment for this field when all the experimental tools are set up, and this is now what are we going to look for next. So with this, I close today, and for tomorrow, it's kind of actually a futurology, and it's, once again, it's very biased because it's what I would like to see. Other people would give you a completely different things. I've mentioned in the end, you know, other things that I know people are interested, but I'm going to talk mostly what I think is interesting. So that's it.
Thank you for the lecture, Thereza. When you started to talk about the beyond half filling experiments, you showed some graphics that shows different cases for. Can you put the slide? I think it's the first experiment. Yeah.
This the incommensurate.
The next one. The one when you show that the pairs they are diagonal or something. I wanted to know what leads to each case. Like
So
for
I'm trying to figure out what. Oh, this is still half filling. Mostly half filling. So this is the incommensurate case, and this is the beyond half filling.
Yes, this one.
Okay. So what is...
I wanted to know, like, sprinkled holes, pi flux theory, which interactions leads to you see each case?
So this is all very new and all very unexplained yet, and I think this is part of why I chose this particular thing. In the most honest answer is I don't know, but I'm glad like nobody else does. So pretty much, the ability, the idea here is that the ability of having, you know, tons of data that you can digitalize and look into it leads to an open possibility of seeing something that has never seen before. And as to what leads, RVB states are really very much discussed in the context of spin liquids and also high TC superconductivity, whether you have pairs of up and down spins that are not necessarily near neighbors, then they can be far apart, but they are somewhat connected. And this, the idea of resonating it's linked here, and then it's going to be linked there, and it's linked here, and then it's going to be linked somewhere. They resonate, they change. And this is something, people have been talking about this for a long time, but I don't fully understand that. Why do they resonate? And here, you asked what causes that. There is no other interaction in there. There's not like when you are in a material, oh, maybe the crystal filled some impurity in the system. It's just what's in there. It's local interactions that's leading to that. And that's very unexpected to me. You see that you have pairs that are linked from, correlations that are resisting distance and are resonating. So this is just to show there is still a lot to understand in this field. And it's quite interesting because people, the Humber model has been there, since the 60s. But there's so much that we don't understand, and it relates to matter in various different ways. So I think it's worth exploring. So the truth is, I don't really know.
Thereza, can I jump on the same question? So the idea in the experiment would be like they have a lot of data that they can do a post-analysis, and maybe they could search for that in some percentage. They would find different things.
And I think it depends on the amount of holes they put.
Okay.
And there is a statistic. So if you have a lot of holes, you see strings. But if you have to fill, you won't, and the amount of doping will lead you to the different cases.
Okay, thank you. Yes.
First, thank you for the lecture. And more about spins. So we had a lecture with Johann Schachenmeier, and we saw the transversizing model. So in the simulations, you select, I want my spin to begin up, all up, or all down. And I wanted to know if I get it right, in the simulations or in the experiment, the atoms, they are all neutral, and then you apply the magnetic field and they come to a line and you hit equilibrium in the system, or is like a snapshot? Because I think they're all hopping in between sites, right?
Yeah, so that's fairly different from the Ising model. In the Ising model, you don't have charge degrees of freedom. The spins are freezed on the sites. They are not allowed to hopping. And here is different. They are allowed to hopping. And another thing I think in these experiments, you prepare your system in a given state. And you perturb, after you prepare it, you put a magnetic field in the perpendicular direction, and you see how it changes from one case to the other. Here, it's not like you're preparing your system in a given state. You set the atoms, and you have some amount of in an up state and down state, and it's either the same or different, and then you're in a given temperature, and you throw them on the lattice, and then you see what happens. It's not like I'm preparing them to be, and whatever state they are, it's the state in which, the temperature allows them to be. So if you have, if you're cold and you have one atom per site, they move around to organize themselves up and down, up and down. It's not like I place up and then I place down. You place them, and they prefer to be in this state than to be disorganized. And you can see this, what happens here is like you have a virtual hopping. This guy comes here and then comes back. And if you have something like that, he cannot, come here because it's Pauli principle excludes. So this is more energetically costly than this one. So when you lower temperature, then you prefer to be in the state because you have this virtual hoppings allowed, and here you don't. And this is why they organize itself in this state. It's not like you put them. You put them in any state, and you wait, and they come to an ordered state if you are low enough temperatures.
Okay, so if you have more hopping, then you increase these correlations, and maybe it tends to
So
equilibrium
it's
faster.
a competition because if you have more hopping, they will move around. So it's a competition between hopping and you, because if you have a lot of hopping, then it's going to wander around the lattice. And it's the you that makes it, I don't want to stay here because it's costly, you're going to pay you, and then I come back. So it's a fine-tuned balance between you and hopping that leads to an ordered state.
Okay, thank you.
Any other question? Yes.
Hello, Thereza.
Hi.
Thank you by the lecture. I got really curious about the 2-point diagram. Which method they used and how costly was it?
So what diagram?
I think is the 80s diagram or phase diagram with two.
Oh,
Yeah.
the 2 points. They used Quando Monte Carlo.
Oh, okay.
The one thing that's curious, oops, I went too far back. So that phase diagram is actually in the 90s. Where is it? Oh, this one here. So this is actually in the 90s. And what happens is she only had access to very small lattice because this is computationally costed. So she had like a 4x4, 6x6, and 8x8. When you do a collapse, something something like that, if you only have, so here is 10, 12, up to 18. So when you have only small lattices, this finite size scaling, it works actually when L is much larger than 1. So is 18 much larger than 1? I don't know, but 4 is not much larger than 1. So and this is something we had to fight with the referee. So she has done it in the past, and you're going to do because you increased the lattice size. And now in 10 years, you're going to increase the lattice size and then calculate again. But, you know, we think now we have reached large enough so that it doesn't change. If you put 20, it's not going to be that different. But it's brave. It was very important then, you know. Somebody had to do it first, and Adriana did it.
Final question? No? So thank you again, Thereza.